Hey everybody, welcome back. We're going to do another problem solving video today. Today we're going to work through parallel circuits worksheet number 2. This is the Wilson sheet that I posted. And again, this stuff takes a little bit of time. So if you struggled on some previous worksheets, it's okay. Go back, redo those questions, submit them again, and eventually we're going to get all of these questions correct. I feel like when it comes to circuits, once you see it, then everything starts falling into place. So again, we're going to do a problem solving video, nice and slow, making sure we understand all the different aspects of circuits, and hopefully this is helpful to you. All right, parallel circuits worksheet number 2. Let's get started. So the very first thing that this worksheet wants us to do is first describes this parallel circuit to us. Keep in mind that parallel circuit rules are different from series circuit rules. A parallel circuit contains one 30 ohm resistor, one 50 ohm resistor, and a 100 volt battery. It includes an ammeter such that it reads the current passing through the 30 ohm resistor and a voltmeter such that it reads the voltage drop across the 50 ohm resistor. Sketch this circuit. Okay, we're going to take this one piece at a time. I always like to start with the battery. There's our battery. We can call this, like it's gave us, this is a 100 volt battery. 100 volts. And then we have two resistors connected in parallel. What in parallel means is that the current has a choice to go through one resistor or the other resistor. We have a 30 ohm resistor, which I'm going to put here, and a 50 ohm resistor, which I'm going to put here. But it also says that there's an ammeter in the circuit such that it reads the current passing through only the 30 ohm resistor. So I have to put my ammeter in this branch here. That way, the ammeter measures the current only through this 30 ohm resistor. Nice. Okay. Now we also have a 50 ohm resistor over here. Okay, we can connect so the current rejoins at this junction and heads back to the battery. And this is a 50 ohm resistor. Before I draw the voltmeter, I want to talk about this ammeter for a second. The reason why I drew the ammeter here is because I want to know the current going through just the 30 ohm resistor. The current can split off. So I want to read the current that's going through this branch of the circuit before it heads back to the battery. Keep in mind, I could also put the ammeter down here and it would still be a valid circuit because it's still measuring the current in this branch of the circuit. I can't put the ammeter anywhere over here because that ammeter would measure the total current in the circuit, not the current through the 30 ohm resistor. All right, I'm not done yet. I also have to draw a voltmeter to measure the voltage across the 50 ohm resistor. And I'll do it over here. You have to remember that voltmeters are connected in parallel because I have to measure the voltage here, and I want to see the difference, the potential difference across this resistor. And this is one possible solution for question 1, part A. It might not look exactly like this, whatever you drew, but as long as you're following the rules, you could still have a correct answer. We need two resistors in parallel, a voltmeter across this resistor, and an ammeter in that branch. Let me draw one other possible solution real quick, just so you can see it. Let's say I have my battery. I could also do this. Feeling crazy. This is also a valid solution. Okay, take a look here now. Let's say this is the 30 ohm, and this is the 50 ohm. So is this correct? Well, we see that the current has a chance to split. We have an ammeter measuring the current in just the 30 ohm branch. Might as well be super clear. Not in the 50 ohm branch, and then we're connected back to the battery. I can put my voltmeter right here. Hey, and look at that. We have another possible solution to part A. I like to draw my parallel circuits like this because I think it just looks a little clearer to me, but if you drew it this way, you're still correct. This is totally fine to draw your circuit in this way. All right, I'm going to erase this. Okay. And there's our circuit. So we sketched it out, we're good. Now we can move on to part B, determining the equivalent resistance of the circuit. Now, as I always say, before you go ahead and start trying to solve out these questions, draw out your VERP table. I'm going to draw my table up over here. Down the rows, we have resistor 1. I want to just move this. This is my 50 ohm resistor. Okay, R1, R2, total. There we go. Then we have V, I, R, P. Perfect. All right. Some of you are holding out. Some of you are really trying not to draw the VERP tables. I promise, this table is going to solve all of your issues with these circuits. By drawing out this table, it just really helps you see what we know and what we want to find and how we can get there. Trust me, use the table. Okay, let's label what we know. I'm going to call resistor 1 the 30 ohm resistor. Okay, resistor 2 is the 50 ohm resistor. The battery supplying the voltage to the circuit is 100 volts. Remember, the battery gives us the total voltage of the circuit for both series and for parallel circuits. All right, and that is everything that we know right now. First thing is we want to find the equivalent resistance of this circuit. That's this cell here. Before I dive in and do that cell, I'm going to take a look at my parallel circuit rules and see if there's anything else I could fill out on this table. Well, one of the parallel circuit rules says that the total voltage is the same everywhere in a parallel circuit. So if I know the total voltage of a parallel circuit, guess what? We know the voltage across each one of the resistors. You can fill that in now. All right. Now, I want to find the equivalent resistance of this circuit. To do that, you look at our rule for parallel circuits when it comes to equivalent resistances, and we have the more complicated equation here. 1 over Req is equal to 1 over R1 plus 1 over R2. I'm going to stop there because there's only 2 resistors connected in parallel here. If there was a third resistor in parallel, I would do plus 1 over R3 and so on. Okay, let's plug in what we know. Our goal is to find our 1 over Req. R1 is 30 ohms. Plug that in. R2 is 50 ohms. All right, testing your fraction knowledge. Keep in mind, you can just plug this into your calculator, take the inverse, and you'll find R over 1 over R. If you take the inverse, you'll find the equivalent resistance, Req. Well, let's work this out. Well, if I want to do this step by step, first we've got to find a common denominator. 1 over Req is equal to, I see that the best common denominator between these guys will be 150. So 150 will be here. And I had to multiply that by 5 to get there. 30 times 5 is 150. For over here, common denominator of 150, I had to multiply this by 3 to get there. So, coming up over here, we get 1 over Req to be 8 over 150. Now, we have to solve for Req. I could flip everything around, or you could cross multiply if you'd rather do that. But REQ is equal to 150 ohms over 8. And 150 divided by 8 will give you 18.75 ohms. And that is the equivalent resistance of this circuit. These two resistors connected in parallel will give you an equivalent resistance of 18.75 ohms. Now always think what that means. By connecting these resistors in parallel, I decrease the total resistance of the circuit. By having these two connected in parallel, it's the same as having a single resistor of this resistance, 18.75. You're giving the current another lane on the highway to go through, another choice, which decreases the total resistance, the total impedance of that current flow. Okay, 18.75. Check your answer. Be very, very careful with your work. This equation tends to trip up physics students often because we always forget to flip over this 1 over REQ. All right. And again, this equation is different from our series circuit rule. Series circuits, its REQ is R1 plus R2 plus R3, a little simpler. But for parallel circuits, we have to use this rule here. All right. I'm going to erase. We'll go on to the next one. All right, so next, we want to find the current through the 30 ohm resistor. That's the reading in the ammeter over here. So we're looking at R1, and the fact that we know two of these values across the row means that we could solve for the other two. We have the tools for that. So looking here, we know the resistance is 30 ohms. We know the voltage is 100 volts. We could solve for the current using Ohm's law here. So we're going to say R is equal to V over I. And this is R1, V1, and I1. Finding the reading in the ammeter. So R1 is 30 ohms. V1 is 100 volts because the voltage everywhere in a parallel circuit is the same. We have two different closed loops. And our goal is to solve for I1. All right, switching this around, 100 divided by 30, we will get I1 to be 3.33333, repeating, and the unit is amps for current. Okay, so we know the current here is 3.33 amps. Cool. That's the next part. We're using the table to help us figure out which cell we want and how we can get there. Okay. So next we want to find, okay, so for the next part, we want to determine the voltage drop across the 50 ohm resistor. And so for that, we could just look and say, okay, if across the 50 ohm resistor, that's R2, the voltage drop you already have down is 100 volts. And you knew that already because the rule for parallel circuits is the voltage drop across these resistors are the same. So what I wrote for this part of the problem is V is equal to V1 is equal to V2. So the answer is 100 volts. That's the voltage drop. You heard it. We already had that cell filled out on our table. All right, next, part E. We want to compare the current passing through the 30 ohm resistor to the current passing through the 50 ohm resistor. Compare means we're seeing if it's the same, bigger, or smaller. So let's figure it out. Let's find the current here. Gonna erase. Well, R is equal to, that's a crazy R. R is equal to V over I. I want to find R2 so I can compare it to R1, the 50 ohm compared to the 30 ohm. So we're looking for 2 in this case. R2 is V2 over I2. Well, we know R2 to be 50 ohms. V2, we filled it on our table, is 100 volts. We want to find I2. Okay, solving for I2, switching them around. 100 divided by 50, I2 is equal to 2 amps. Okay. Plug that in here. But remember, that's not what the question asked us. It didn't ask us what the current was through the 30 ohm resistor. We want to compare the current through the 30 ohm resistor to the current through the 50 ohm resistor. And we can see that the current through the 30 ohm resistor is greater. 30 ohm resistor has more current. So by setting up these resistors in parallel, you can see that we draw different currents through each one of the resistors. So we're drawing 3 1/3 amps through this branch, while we're only drawing 2 amps through this branch. This has less resistance. The current is going to want to flow through the path of least resistance. So there's going to be more current flowing through this branch where there's less resistance than through this branch where there's more resistance. That's one of the cardinal rules of circuits. Current flows through the path of least resistance. If I set up, kind of going off script a little bit, if I set up a wire that kind of just attached from here to here, this is what we call a short circuit. So what happens here is because now we get to this junction, the current is going to want to flow through this spot here because there's no resistance there. There'll be effectively zero current through these branches, and all of the current is going to flow right back to the battery. Short circuits are dangerous. When you drop your phone in water and they say don't turn on your phone, just stick it in rice to get the water out, what's actually happening is the water is getting into the tiny little circuitry of your phone, and those droplets are causing short circuits in a lot of different places in your phone. So sometimes you can turn on your phone and everything works okay, but sometimes you turn on your phone with those water droplets inside, creates those short circuits, and that's what starts burning out the tiny little components inside of your phone. So that's why it's good to get those droplets out so we're not creating any of those short circuits and burning out any of the components. Okay. Another thing, again, off script, that I wanted to mention, I want to take a look at the meters real quick. Let's get rid of these nodes. Okay. We always say how we're connecting our meters, but we never really talk about how those meters affect our circuit, right? Well, I'm putting this ammeter here to measure the current through that 30 ohm resistor. So what resistance would this ammeter have to make sure that we're not affecting our circuit in any way? We only want to measure the circuit. We don't actually want to change any of the specifications of the circuit. So this ammeter needs to effectively have zero resistance to make sure that we're measuring the correct current in this circuit. Imagine this ammeter had a resistance of 30 ohms. You would see that would affect the current in this branch. So ammeters have almost no resistance in order to make sure we're measuring the right current. But voltmeters, on the other hand, imagine voltmeters had no resistance. Then the current, why would the current want to go through the 50 ohm resistor? It would just go through the voltmeter. Voltmeters have a super high resistance to make sure it doesn't draw any current through the meter. But that way it can only check the voltage across without taking any current away from the circuit. A little bit of a glimpse into how these meters work and how they measure the specifications of our circuit. All right, that's enough of a tangent. Let's get back to what we were doing. I'm going to erase. The next thing we want to do is you want to compare the voltage drop across the 30 ohm resistor to the voltage drop across the 50 ohm resistor. So we're comparing the voltage drop 30 ohm and the voltage drop 50 ohm. The voltage drop is exactly the same based on our parallel circuit rule. That's the big change from parallel circuits to series circuits. The rules swap for these two columns here. The voltage is exactly the same. And with that, we're done with this problem. I said it before, notice there are still cells empty. You can fill in the cells if you want, but we answered everything that they wanted us to answer about this circuit. So we are good for now. We're going to move on to problem 2. I'm going to erase, and we'll get back to it. Break time. All right, welcome back. Problem 2. Over the little break, I was looking at myself in the camera, and I got a little quarantine fuzz going on. I got to trim up. All right, question number 2. We want to find the equivalent resistance of this circuit that's given here. We have a 12-volt source. We have an ammeter measuring the current through the 20 ohm resistor and this 30 ohm resistor. What is the equivalent resistance? Okay. So, like I say, I would use the verb table here, but you might have an idea of where this problem's going. We have a 20 ohm resistor, 30 ohm resistor. We want to find the equivalent resistance, that's the total resistance of the circuit. And we have a 12-volt source. To find this cell here, if we know the two resistances above it, we can use the equivalent resistance rule for parallel circuits to find this spot here. That is 1 over Req is equal to 1 over R1 plus 1 over R2. Remember, you can only use this rule for parallel circuits. The other one applies for series circuits. Equivalent resistance. R1 is 20 ohms. R2 is 30 ohms. Solve for Req. So we'll get a common denominator here. I see that 60 is probably going to be our best bet. We're going to say 60 on the bottom, which means I'm going to multiply it by 3. And I want 60 on the bottom here. Multiply this by 2. Gotta love those fractions. Okay. So we end up with 1 over Req is equal to 5 over 60. Do not report your answer as 5 over 60. That's incorrect. That's not the equivalent resistance. That's 1 over the equivalent resistance. We have to solve for Req equals. So flip everything around. Req is equal to 60 over 5. Well, 60 over 10 would be 6. So 60 over 5 should be 12. Okay, and that's the equivalent resistance of the circuit, 12 ohms. All right. Being able to manipulate these things mathematically in your head could help you kind of quickly predict what the answers should be. You might not be able to predict exactly what number it is, but you should be able to predict a roundabout where the number should end up. Helps you check your work. Okay, now for the next part of the problem, we want to find the current reading in the ammeter for this circuit. That is the current across the 20 ohm resistor. That's R1. Let's erase. So maybe we didn't need a verb table for this part of the question, but we do need it for this part. Okay. So I want to find the current reading in this ammeter. I don't have enough information to get there yet. Like, I don't have enough filled into my VERP table to get there. So we have to look at our parallel circuit rules. What do we know that we can fill in by following those rules? We know the voltage across all of these resistors have to be exactly the same. 12 volts all the way up. Now we have enough information to figure out the reading in the ammeter. 20 ohm resistor. Let's figure it out. By having V and R, we could use Ohm's law to figure out I. Okay, and this is R1, V1, I1. Going across, we know R1 is 20 ohms. We know V1 is 12 volts. What's I? Okay, flipping things around, solving for I, you'll see that I1 is going to be 12 divided by 20. 12 volts divided by 20 ohms. And that is going to be equal to, I got 0.6 amps. And that goes here. All right, that's our answer for that one. And we're all done with that circuit. Again, we're leaving a lot of spaces blank, but we don't need them. We're just using the table to help us see what we want and how we can find what we would like. We have one more question to go. We're gonna erase. All right, last question. A set of resistors is connected in parallel. Adding resistors to this circuit in parallel with others will do what to the equivalent resistance? So, when we have these resistors in parallel, if I add more and more branches, what does that do to the total resistance of the circuit? As I keep going. Well, intuitively, we said that by adding more and more resistors in parallel, we're opening up more and more lanes on our highway. So by giving our current more choices to go, we actually end up decreasing the equivalent resistance of the circuit. And that's actually shown by this relationship as well. Okay. I might not be able to really see it mathematically here, but by adding more and more terms, we're decreasing the value of the equivalent resistance. When you have a bunch of resistors in parallel, the equivalent resistance is always going to be less than the value of any one of those individual resistors. So the correct answer for number 4 is choice 2. Decreases the equivalent resistance of the circuit. So by adding more and more resistors in parallel, if we decrease the equivalent resistance, we actually end up drawing more and more current out of the battery, or whatever our voltage source is. Okay. All right, and with that, we are all done with this worksheet. I hope everyone's doing well. I hope you guys are feeling okay with this problem solving. We're going to have one more circuit assignment by putting all these things together, different series circuits, different parallel circuits. And by the end of that assignment, hopefully we've mastered circuits. And next time you see me and my face, we'll probably be talking about magnetism. Get ready, and I'll see you in the next video.